So in this video, I wanted to focus on an important topic when it comes to programming in general, and that is the topic of big O notation. Big O notation essentially allows us to quantify our code and tell us how efficient our algorithm and codes are. This is important because when you're designing large-scale applications, every second is going to count. So having an algorithm or a piece of code that runs faster than others is going to be important, and we need a way to quantify that, and Big O allows us to do this. So in this video, we're going to talk about the four levels of big O notation. That is O of 1, that is log n, that is O of n, and O(n) squared. So what this big O means basically is, so we have our O, and then whatever is in parentheses is essentially the runtime of our algorithm. So O1 means it is constant. So essentially what that means is no matter how big the input gets, no matter how big, no matter how small, the runtime, the time it takes for the algorithm to complete, will be constant. So if I have a million items versus one item, the time will be constant. Log n will be logarithmic. So that'll mean as the input grows, by the way, n is the size of our input. So as n grows, our runtime will expand logarithmically. So this is actually a pretty good runtime because you'll notice when I show you this graph, log n is great because when we have an input of n, it'll grow quite fast at the beginning, but it'll taper off as the input grows and grows and grows. So O log n is actually a really good runtime. O of n is just linear. So let's say I have a million items in an array, and I need to go through each item. That's going to take a million times. So linear basically is the runtime will scale linearly with the size of the input. So it'll grow linearly according to the size of the input. And then lastly, I wanted to focus on O(n) squared. This is just quadratic. So as the input, so essentially if we have an input of 10, our runtime will be 100. So our input increases quadratically. So this is quite slow, and we try to avoid these types of big O notations, these runtimes. And there's other runtimes like O(n) squared, O(n) factorial, O2 to the n. These are much larger. We won't go over this in this video, but just know that that exists, and those are much slower, and we essentially really want to avoid those at all costs. So just to show this to you in graph form, so here we have an O of 1. This is constant, this graph here. So we have y equals 1. So essentially what happens here is you notice that no matter as far as we go, it's always constant. It doesn't matter where we are in terms of our input, how big our input is, it's always constant. It's always 1 in our case. If we put 100, same thing. We just have to zoom out a little bit, and you can see this is constant. This does not change as the input grows. It remains constant. This is why this is the best runtime, because despite having, let's say, a billion items, we always want to think about big O as really large input. We don't want to think of it as like 10. We want to think of it as a very large input. That's what really matters. So if we had a billion items, even if we had a billion items, it would still be a runtime of 100 in our case. This is why O of 1 is the most optimal runtime. But it's very unlikely that you're going to have an algorithm that runs in O of 1 time if you're doing complex things. So the next one we want to talk about is log n. So if I do log n, let's make it a bit bigger. So let's make it log 10n. No, let's go 100. So I need to zoom out a little bit. But this log n, so you can see that it grows quite significantly right here. So right here we have a pretty big increase. It's a sharp increase. However, you notice that as n grows, it starts to taper off, and we'll get to a point where it doesn't grow significantly at all. It just stays. This is why log n is really good, because you notice that it increases sharply, but we'll have a logarithmic runtime, and that's why this is so optimal, because despite n being so big here, 3,500, these are actually quite small, but if we think of them as very large numbers, despite this being 5,000, 500 more barely gives us an increase. So that's why logarithmic is so significant and a very good runtime. Now next would be O of n. So let's say y is equal to n. So with n, what happens is it grows linearly. So if we have 500, if we have an input of 500, our runtime is 500. 500, whatever we want to quantify, seconds, milliseconds, whatever it may be. But it grows linearly. So obviously it's not as good as O of a constant, so O 100. And like I said here, we want to think of these as really big inputs. So 100 isn't the best example, but you can see that as this grows, it's growing linearly, this grows logarithmically, and this stays constant despite the input size. And lastly, let's do O(n) squared. So y is equal to n squared. Now we're going to ignore the negative portion of this graph, but you'll see that it's much, much steeper. So this is why it's not as optimal as O of n, because it grows quadratically. So obviously it's not as optimal as the previous algorithms. And of course, there's other ones like O of n cubed. You can imagine how big, how slow that becomes as the input grows. Same thing with O of n factorial and O of n and O of 2 to the n. Just to go over a few examples here, I wanted to talk about what are some examples of some big O notations inside their code. And also, one thing I wanted to mention before we talk about this is when we have constants inside of our big O, we actually drop the constant. So if we had O of 100n, it would actually be O of n. And the reason for that is we always want to think of big O as very large value. So let's say we had a billion items. If we multiplied that billion by 100, that 100 would actually be quite insignificant in relationship to our input size. So we actually drop constants because they don't have a large effect on our algorithms. So I'll show this while we're going through the code, but for example, it would just be O of 1. So O of 1, like I said, is just a constant time. So it doesn't grow with the input. So if we had a billion items versus 1 item or 10 items, it wouldn't matter how long, it wouldn't matter how big the input is. It would just grow at a constant time. So here we're just accessing a number from our array. This is a hypothetical array that doesn't exist, but let's say we wanted to grab the 12th index item from this array nums. This would be O of 1 because it doesn't depend on the size of the array or the size of the input. We could do this for any array. If we want to grab the millionth item, the billionth item, the 10th item, the first item, it wouldn't matter. This would be essentially O of 1 constant. Next is O of n. So O of n grows with the input. So here, if we had, let's say n was equal to a billion, it would take us a billion iterations to loop through this loop. So the amount of times we loop through, the amount of times we do a loop is dependent on the size of n. So the runtime grows with n essentially. So that's a good example there. Then this is O of n squared. Now the reason why this is O of n squared is it's two loops, but they're nested. So when you have something inside of a loop, when you have another algorithm inside of your inside of one loop, you essentially need to multiply them both. So here we have one for loop, and then another for loop inside. So if we have something inside of a for loop, we essentially multiply the operations. So this is O of n, this is also O of n, and O of n times O of n becomes O of n squared. And that's why it's like this. So I think a good use case would be looping through a 2D array. So we loop through the rows, and then loop through the columns, and this would essentially be whatever we wanted. And obviously, if I want to add another for loop inside, then we'd have to consider that as well, and then that would become O of n cubed. So if we put anything inside of a for loop, we essentially need to multiply the piece of code or the algorithm, and that's why this becomes O of n squared. Now, like I said, we want to drop constants. So that's a great example is this guy here. Now, actually, this is not the same as this. The reason being is we have two for loops, just like this one, but however, these are not nested. These are individual for loops. So we don't actually multiply them, we add them. We add each operation. So we have O of n here, and then O of n as well. So technically this is O of 2n, but like I said, we actually drop constants because they don't actually have a big impact on the runtime of our algorithm. We always want to think of big numbers. That's why they don't have a big impact. So because of that, we can drop this O of n. We can drop this O of, we can drop the 2 here, and this will essentially just be O of n for really big numbers, of course. Now, this can also apply if we keep doing this. So if I keep doing this, now you'll probably think that, wait, this surely must be bigger than this one here. This surely must take longer. And although, yes, maybe for small inputs it could, but if we had like a million or a billion items, this O of n squared is considerably longer than just several for loops. So this is important to remember. We want to try to avoid nested for loops as much as we can. Sometimes we can't, but we would like to avoid nested for loops if possible. Now, lastly, I want to talk about O log n. So log n basically is, in computer science, we usually think of the logarithm. You might have learned in math class that we think of the logarithm as base 10. But in computer science, we think of the logarithm as base 2 most times. So what happens here is we loop while this is greater than 0. So let's say n was equal to 100. So on the first iteration, we have n is equal to 100. Then we divide it by 2. this becomes 50, this becomes 25, the next one will be 12.5, and so on. And you can see this drastically decreases the amount of iterations we do. So this grows logarithmically. So instead of doing, so if we want to loop through n 100 times, so O of n 100 times, it would take n, it would take 100 times. But here we're actually essentially cutting it in half each time, and that's why this becomes O log n, because it's that much more that much more efficient. And log n is also in algorithms such as binary search and binary search trees, and really anything binary search related, you're always going to have a log n runtime. So this is one of the best algorithms, best runtimes you can have, because we see that it gets cut in half. And here it's base 2, but if I divide this by 3, it would be base 3, divided by 4, base 4, you get the idea. But log n is a great runtime, a great big O, and if you can achieve this, then your algorithm will be quite often quite fast. So now, just to illustrate this binary search algorithm that I just talked about, I just want to show you what it would look like in code and just kind of demonstrate why this is log n. So let's say we had an array and we're looking for a number inside of that array, and it's called target. Now, this is going to be an ordered list, so the numbers will grow. The first numbers will be the smallest, and the last numbers will be the largest. So what we can do here is we can use the binary search algorithm. So we'll define a start and an end, and then we can loop while this start is less than or equal to the end. So the binary search algorithm works in the way that if we have a list, let's say 1, 2, 3, 4, 5, and 6. Let's say we're looking for number 4, or let's say we're looking for number 6. What it'll do is it'll grab the first item. So it'll start the first index at 0, the last index at, so in this case, there is 6 elements, so the 5th index. It'll keep looping until a condition is met. So to get the middle element, so here we go, the middle of 5, the middle of start plus end, so 5 plus 0, 5 divided by 2. In Java will just end up being 2, so we go 0, 1, 2. So it'll grab this third element. Now it'll check. So first of all, is it the target that we want? No, the target is 6, so it's not found. So if we found it, it would be true. Otherwise, we check. So we say num's middle is it equal to target? Is it less than target? Sorry. So here we have 3. 3 is actually less than our target, so that means we need to increment our start to middle plus 1. So now our middle will be 4, and this else doesn't get met. We keep looping until we find this 6, and eventually we will find the 6. And you notice that this essentially cuts, instead of looping through it individually, like looping through it linearly, we can actually just loop, we can just check only the numbers that we need to check. So we just binary search. So we split it in half. So we started in the middle. Okay, now we split in half. Now we split in half. We split in half. And this will essentially become a runtime of log n. Now, this is really good for really big inputs. So if we had a million items, we'd only need to search it 20 times, I believe, for binary search. So it's very efficient and much more efficient than O of n. So I hope this example helps a little bit. So I hope you guys were able to take something away from this big O notation tutorial. It's important to understand why your algorithms are faster, why our algorithms are slower. So having an understanding of big O is really important. Hopefully these fundamentals taught you something, and you can think about this when you're writing your own code. Anyways, thanks guys.